be a bit quicker in the flows of surfaces talk, but as it turns out, I was really just filling the allotted time, and now we really start the second topic, which is the same topic except slightly more advanced. Wow, it's clean. This is clean today. Right, so the topic is unipotent dynamics. Subtitle, measure classification. And I want to give you the three major theorems . First one is Ratner's theorem / Stani's conjecture / the measure classification. The titles are almost as long as the statement. Let X be G mod gamma. Let U, UT, T in R be one parameter subgroup, one parameter unipotent subgroup. Let me finish the statement and then come back to the assumptions. Then all U invariant and ergodic probability measures are algebraic. So whatever all these terms mean, seems like a nice statement. Right, what's a unipotent group element? Unipotent group element. Suppose G is in G and G is in S sub E. We have a linear group. Then G is unipotent if G minus the identity is nilpotent. Nilpotent means that all the eigenvalues are 0. Unipotent means that all the eigenvalues are 1. Which means inside SLDR you may conjugate this element and make it upper triangular. So we have, or lower triangular if you want, yes. Yeah. Of course, the horocycle flow that we have been talking about is an example. Of course, the horospherical actions that we have been talking about in higher dimensions are examples, except that they may not be one parameter. And you might say, well, one parameter, two parameter, what's the difference? It makes a lot of difference, because the argument that we did yesterday using mixing works for the horosphere, period. It doesn't work if you have a subgroup of a horosphere. And that really makes a huge difference in the amount of work that goes into the proof of the statement. So the horospherical action, it really is the argument from yesterday plus the non-divergence, if you want to do it a bit more general, for non-convex quotient, and that deals with it, and that deals with all the G mod gammas, and that's it. This theorem, well, is a different entity. It's somehow much more complicated, and I can't explain the proof of that, but I will try to give you special cases where we see some of the complications, some of the steps that we need to do in general. And somehow the goal is to present you the tools that appear in this general strategy of proving the theorem. But then there's a difference between giving you all the tools to prove the theorem and proving that all these tools are sufficient in all cases. The latter I will not do. Okay, so Yes, one parameter is here. As usual, we just have this kind of thing. Unipotent I explained over there. U-invariant and ergodic probability measures, we know what those are. What are algebraic measures? Those are H measures of finite volume orbits. Right? So algebraic means this measure mu is equal to mxl for some closed connected subgroup, which of course is in G and of course contains U. It could be equal to G, it could be equal to U. Equal to U would correspond to a closed periodic orbit, equal to G would correspond to the H measure, which quite often is ergodic. We have discussed that. And this measure, I maybe should say a bit more about. XL is an orbit, right? Every orbit is isomorphic to a quotient of the group, namely L mod the stabilizer of the point X within the group L. If X would be the identity element, then this stabilizer would be the intersection of L with your discrete subgroup. And if X is not the identity coset, then you first have to conjugate your discrete subgroup by the corresponding point corresponding to X, and then take the intersection, and you get this quotient. This is completely general, abstract, but when I say algebraic, I mean that this stabilizer is a lattice inside the group L, so that this quotient has a finite, hence I can normalize it, a normalized L-invariant H measure. And this L-invariant H measure I can then consider via this isomorphism as a measure on XL, and hence, because XL is sitting inside capital X, as a measure on X. That's the natural L-invariant measure on this L orbit. And there may such things that may exist, such nice orbits for some nice subgroups. And the statement is, if you have a U-invariant ergodic probability measures, it's one of those. And the assumption is that gamma is discrete in this theorem. So it's very nice. It's a very nice rigidity result, right? Because the assumption on the measure are very little in some sense. Ergodic and invariant. We know they always exist. We know they have some information about the behavior of orbits. And then the conclusion is they're really part of algebra in some sense. And that's the surprising thing, that's the rigidity result. Theorem, Ratner's equidistribution. Theorem that X be G mod gamma with finite volume. Let little x be in capital X, then little x is generic for some U invariant and ergodic probability measure on X, i.e. 1 over t integral from 0 to capital T f of x u minus s es approaches integral f d m, where m is some nice algebraic measure by the previous theorem, and actually it's the same base point as t goes to infinity. And this is for all f in CX, as yesterday. So in particular, this equidistribution theorem says that you have recurrence. If you start somewhere under unipotent flow and you use this dynamical system, the unipotent flow, it's coming back to the base point with positive frequency. you don't quite know what frequency. I mean, back means to a neighborhood of the base point, of the starting point. Which frequency really depends on which measure you will see here and which group you will see here. And the group that you will see here depends on the base point, the starting point. We have discussed this again already in the host cycle case. Some points happen to have periodic orbits, some points happen to have non-periodic orbits. And it might be generic for the whole group, for the whole space. And the difference here is now that this L has even more possibilities. There could be more different L's showing up than in the previous discussion for horocyclic and horospheric collections. Theorem. So that's again Ratner's orbit closure theorem. It's Ratner's conjecture. And that's really where it started in some sense. This conjecture motivated all of these theorems and conjectures, and the Raghunathan conjecture itself was motivated by Oppenheim's conjecture, which was solved independently by Margulis, but is actually a corollary of the Raghunathan conjecture / the Ratner orbit closure theorem. Okay, so what's the statement? Let H in G be generated by one parameter unipotent subgroups. Then XH closure, the closure of an orbit, is always an orbit of a group, and to put more constraints on the possible L's here, XL has finite volume. So again, the orbit closures are algebraic, they are orbits, and they are algebraic in a very strong sense. They support an algebraic measure as in the theorem over there. And I will not talk about this theorem and that theorem. The logical order is somehow like this, but there are additional arguments that go into these steps. Really have to work more for this step. This step is much more work than this step, I think. And here what goes into it is sort of, it's called linearization. There's quite some work that you have to do, and you start by looking at this expression here. You start with the ergodic average, and you know that such an ergodic average converges to the integral with respect to an invariant measure. You've seen that 2 days ago. That we always get an invariant measure, but we get an invariant measure, maybe not an ergodic measure. So you somehow have to work and rule out that there are more than one ergodic components appearing in the ergodic decomposition of the limit measure, which you don't know. And there's lots of interesting steps needed to do that. And now I stop talking about that and start talking about that. Are there any questions?
You do not assume finite volume.
Not in this statement. I assume it here and here. I should have said that, but yeah. Here and here you need finite volume, not in the measure classification. I will assume it because it simplifies my life a bit. Because whenever I see a horosphere, I can say, we already talked about horosphere. Done. But in general, you wouldn't have to. let me start.
Why in the last theorem didn't you you took a general H and not a one parameter? And
Because it's more general.
I mean, also more general. Okay.
So difference is this theorem would be the same with that here, in that generality. The middle theorem, it's hard to phrase what it would mean because maybe this H is not amenable and then I don't have such averages. But if the H is itself a unipotent, maybe not one parameter, but a unipotent subgroup, then I could do it the same thing.
And when you write the implication, you mean that the one parameter version...
Even the one parameter version implies that theorem, yes. So somehow the one parameter case is the most important case because it's the most difficult case and it implies the others somehow. Maybe not the equidistribution of the others, then you really have to do the whole argument again, but it's the most difficult case in some sense. Because if you're one parameter, then the distance to your group is the biggest, right? And if you have more and more invariants, if you start with more and more invariants, then it's easier to show properties of it, because you have fewer possibilities. But if you start with one parameter thing, it's the most complicated thing to start with. Okay. I want to start talking about a special case and give you the precise assumptions. X equal G mod gamma, just gamma discrete, no assumptions. Let H in G be a semi-simple subgroup without compact factors. Take H isomorphic to SL2R. I will just talk about SL2R. The argument is the same for in a more general context. Then every H invariant and ergodic probability measure is algebraic. That theorem is easier to prove. We will finish it today, maybe even in this hour. It's easier to prove, but it's less useful again because of the lack of amenability. This H is not amenable, so I don't even know how to produce such invariant measures. But the classification of them is easy. Right. I list you the tools that we are going to use for this theorem. If H is SL2R, it acts semi-simply on finite dimensional linear spaces, vector spaces. i.e. H acts on some V, and if W in V is H invariant, then there exists a set, another subspace of V, such that V is the direct sum of W and Z, and Z is H invariant. You might say, yeah, isn't it always like that? Well, the point is that it's precisely not like that if you have a unipotent flow. If you have a unipotent element acting. Right? Think of a unipotent. How does a unipotent look like? That's a unipotent. Now think of an invariant subspace here, other than the whole space. depends on row or column, which one you have chosen. Anyway, let's say column. This is invariant subspace because it's precisely the eigenspace for the eigenvalue. And it's precisely not true for this that you have an invariant complement. So for unipotence, this statement is not there, and that's one reason why this theorem is much easier to prove, namely because you have invariant complements. But so that's one tool, and that's part of an introduction to Lie theory or representation theory of Lie groups. And it's really, for SL2, it's a basic sound that you all should know.
So it's basically Weit's unitary trick.
Say that again?
Weit's unitary trick.
Yes. So what he's saying is that SL2 is basically a compact for that statement. You can just switch SL2R to SO3, it's more or less the same group. And for SO3 it's completely trivial because you can always assume, if you have a finite dimensional action, that it acts unitarily and hence the orthogonal complement does the trick. And the trick is precisely that you can do this switch. And that's called Weil's unitary trick. Okay, that's the first tool. The second tool, we need generic points. But I already told you that H is not amenable, so what does it mean we need generic points? Well, that's easy to fix. H contains U, which is isomorphic to this group. Right? I'm assuming H is SL2R, and in SL2R I have this group, so H contains a copy of this group. And U acts ergodically. Why? Well, because we have proven it. Whenever H acts, and it acts ergodically, it acts mixingly. Whenever it acts mixingly, this unipotent subgroup acts mixingly, but then it acts ergodically. So this is a corollary of Moore. Hence we have generic points for U. We just use U to talk about generic points. But then I want a bit more than generic points. Almost every point is generic. But I want something else. Definition, a set K in X is a set of uniformly generic points if the generic property, the equidistribution, holds uniformly on the set K. That the convergence happens uniformly on the set K for every continuous function. If for every epsilon greater than 0, for every f in Cx, there exists a T naught such that for every x in K, not an x, every x in K, 1 over T integral 0 to T f of x u minus s ds minus integral f d mu is less than this.
What's the role of T0?
T more than
For every T bigger than 0. That was the comment, yes, thank you. Lemma. For every epsilon, which of course is now a different epsilon greater than 0, there exists a k in x. M and mu of k is bigger than 1 minus epsilon, and k is a set of uniformly generic points. So it's not true unless you're uniquely ergodic. It's not true that almost every point belongs to a uniformly generic set of points. Well, that's true, but the uniformly generic point of sets is changing. If you want a uniformly generic point, a set of uniformly generic points, if you want such a thing, you have to give away a bit of the space where the uniformity doesn't hold. But it's only an epsilon that you have to give away, and the proof is apply the point-ergodic theorem to each continuous function from a dense subset, and wait until, for every such thing, wait until the theorem kicks in. I mean, for every continuous function, you know that the convergence holds. And for the first continuous function, figure out at time t0, so that this statement is true on a set of measure 1 minus epsilon prime over 2. And then for the second function you do it over 4 and so on, so it's a geometric series and it's very easy to do. I will not prove that. It's in the notes. Minor amplification of the previous statement that almost every point is generic. So that's a tool that we are going to use. And then we need one more. Tool number 1, tool number 2, tool number 3. And one name that is used for this argument is H principle. Maybe you could also call it polynomial shear. Into step mu. Maybe it's time to define what step mu is. Step mu is the set of all group elements so that G preserves mu. Let me give you a lemma, which is very easy to prove, and it's not quite yet the polynomial shear statement. Suppose x G mod gamma u mu as above, to have an ergodic U invariant, an ergodic probability measure on some x. Suppose y equals xg, inverse say x are both generic points, and something else. G is in the centralizer of the unipotent group. That's a pretty restrictive additional assumption. Two generic points close by, that's easy. I mean, I didn't say close by because it's not irrelevant, but not relevant to our current thing, but we will later think of G very small. But this is a very restrictive assumption, but still it implies something interesting. G is in the stabilizer of mu. It preserves the measure. The formal proof is in the notes. Let me draw the proof as how it happens in space. And maybe play it with colors as I go. I have this point x, and this point x has an orbit that I understand, and I don't want to draw it too long because it becomes too messy. It actually distributes in the space, right? With respect to the measure that we're currently thinking about. And now we have another point, y, and usually if you start with 2 points that are close together, they stay close together for some time and then they do something completely different because it's an interesting dynamical system. It's not just isometric, which has to do with our metric being left invariant but not right invariant. Our action is the right action, so it's not an isometric action on our space. Now, this assumption makes the picture look like this. The 2 points stay close together and travel close together, parallel to each other all the time. Because if you push this x by u of t and this y by u of t, the assumption that the g and the u commute tells you that the two image points differ by the same g as previously. The green line approximates the measure, the red line approximates the measure, but you get the red line out of the green line by pushing by g. So mu is preserved if you push it by g. The formulas you're going to write down, it's quite easy calculation. Okay, now there's no shear yet in this statement, and this lemma is just to deal with the case where there is no shear. If I take 2 points and my g is commuting with my flow, in some sense I already have some information. So let's now consider the opposite case, where the difference of the 2 points is not in the centralizer. Why do I bother about this group? The goal of the whole argument is always to show that you're supported on a single orbit of this group. Or another way around, if this is not true, then you want to show that your group actually is bigger than what you thought before. Our aim is always to try to increase the stabilizer, to make the stabilizer bigger. And if we can manage that, that's good. If we can keep managing that, then we, run into a contradiction at some point, which means at some point it stops, and hopefully it stops precisely when we know that our measure is supported on one orbit of our stabilizer group. That's the goal. And then we sometimes also just put a circle there, and that's even easier to do. Now, suppose now y is equal to x inverse, but g is not in the centralizer of the group U. Then I want to do the following. I want to hit both x and y with the unipotent flow. And as always, I introduce in the middle, or as often I introduce in the middle again this term. So if I change both points by the same unipotent element, and I think of my g as a displacement between the two, g is the displacement between the two, it tells me how to get y out of x. Then, after changing both points by the same unipotent flow, the conjugated element is a displacement for the new points. Where I either said a displacement, because at some point this conjugated element will get big, very big, and then again it may not be the smallest displacement. But for a long time, maybe if the g is very small, for a long time this should be the smallest displacement between the two new points, this point and that point. Now, there's something very nice about this expression here. And that really is the key ingredient for all of these theorems. This is a polynomial. How do you get a unipotent flow? there's only one construction of a unipotent flow. You take a nilpotent element of the Lie algebra, then multiply it by T and take the one parameter subgroup corresponding to this nilpotent element. So X, T, W is now a one parameter flow. And let's just think of a linear group. So G is inside SLD, R, and then this W is inside little SLD, R. So it's again a matrix, because this sits inside met TD, R. So when I say nilpotent, let's just say it means that this W is a nilpotent thing. And then the exponential looks like this. It's identity plus T times W plus T squared over 2 times W squared plus and so on, right? However, it stops because the W is nilpotent. Some power, the D power of W is equal to 0. So ut is a polynomial. But if ut is a polynomial and ut inverse is a polynomial, which it is, then this product is a polynomial. For the geodesic flow, nothing like that is true. For the geodesic flow, this expression is an exponential function. Because you see, in the parameterization of the one parameter subgroup of the geodesic, you see the exponential in the beginning already. But for the homocycle flow, for other unipotent flows, this is always a polynomial. And now think of the case, what's going on if this G is very, very small? We will later let G go to the identity. Then this G is very, very small, and then this polynomial is very, very small for a long time. It's not constant, it's not the constant polynomial, because if it's the constant polynomial, we are back in this case, which we already understand. So we always assume that the G is not in the centralizer, and then this is not the constant polynomial. But it's a polynomial that's pretty boring for a long time, because it's almost identity, almost identity, almost identity. So the key idea is to use Zeitraffer, time-lapse. You don't look at this polynomial in the normal time frame. You change your time frame according to the G, and you wait, you renormalize, however you want to phrase it, in such a way that this polynomial becomes interested in the time window that you think about. So choose some t equals t of G such that P of tau equals U tau T G U tau T inverse satisfies P tau, that's now a polynomial with a new variable, minus the identity, norm of that is equal to 1. That's what we want to do, right? And the picture is the following. We have our...
Well, tau is, you consider it as a variable that runs...
It's my new independent variable.
But the norm is the norm.
Right, thank you. So it doesn't matter. Why? Because, I should still say what it means, but it doesn't really matter precisely what it means, because this is a polynomial. What's the degree of the polynomial? Well, it depends on what the degree of nilpotency is. And then maybe you have to square that, because you take a product of two such expressions. So it's a polynomial of a fixed degree, with a total upper bound depending on d. We really don't have to worry about the degree. Which puts this polynomial into a finite dimensional vector space. It's inside the finite dimensional vector space of all polynomials taking values inside met ddr. with degree bounded by an absolute number, depending again on D. So it's a finite dimensional vector space. And now, who cares? I don't care which norm you take on this finite dimensional vector space. Take one of them. They're all equivalent, right? It doesn't matter. For instance, let's make it concrete. Let's take the Supremum's norm on the unit interval, where we take whatever Euclidean norm on met dB. That's a norm on this finite dimensional vector space, and with this norm I make that assumption, and that defines me the parameter t as a function of g.
Do you take the difference from 1 or g?
So this is an element of this vector space, where tau is my independent variable, the variable of the polynomial that I'm considering. This is the constant polynomial, where the tau doesn't appear, and then I look at the difference. Why do I subtract the identity? Because at 0, p has value identity.
At 0 it is
Say it again?
at
G.
0 it is G.
If tau is equal to 0, it's g, yes. But g is close to the identity. I always think of g close to the identity. Yes, it's not equal, but very close to. So I don't want that value to influence my t, because that value is not interesting. I want to wait until I see something else. So I subtract the identity. And if g goes to the identity, p of 0 minus the identity goes to 0. So this term, the constant term of this polynomial, is sort of neglected by making this
So
normalization.
less than 1?
Equal to 1. That's what I want. Why can I do that? If I take a polynomial, think of a parabola, and you change a parabola like this. Right? And then you change the time. Then you can make it look like this. And whatever norm you have chosen, this will have a large norm, because it's a very complicated parabola. And when you change the time at some point, you will have this assumption. And that's a function of my displacement.
So your capital T just boosts up the coefficients.
Yeah, time lapse. Yeah, it boosts up the non-constant coefficients. And the constant coefficient is tiny anyway, and I subtracted it more or less, so it's irrelevant in the discussion. And every other coefficient gets amplified by the t, because I think of t bigger than 1. Because I think of g being close to the identity. So, that's time-lapse photography, Zeitraffer, which I do. I just speed up the whole thing until, and I stop, where I just see the interesting thing develop within 10 seconds of my new time variable. Okay? So, this is what I will always do from now on. This principle is very important for what follows. And now I want to phrase the polynomial shear statement. Proposition. X g mod gamma u mu as before. Let yn equals x gn inverse, doesn't really matter, xn be from a set of uniformly generic points. Suppose Gn is not in the centralizer, because if it is, I want to apply the previous lemma rather than this proposition. Not. define Tn equals T of Gn as above, right? I have a sequence of displacements for a sequence of tuples of generic points, and I can define these parameters Tn, which define just speeding up. So I get these new things. And suppose, as I was saying before, Gn goes to the identity, which equivalently means that the Tn goes to infinity. I have to speed up more and more to get away from the identity, because if I'm very close to the identity and conjugate, I stay close to it for a long time. One more suppose, but this last suppose is essentially without loss of generality, because, let me write down what suppose is, Pn of tau, which is my speeded up polynomial, u Tn tau Gn, yeah, I'm inconsistent about the -1, let's kill it from here and here. Doesn't matter. U Tn tau inverse. That's now a sequence of polynomials that all have norm 1 within a finite dimensional vector space, which of course has the property that the unit pole is compact. So I can choose a subsequence so that this sequence of polynomial converges to some unit polynomial, P of tau. That's a loss without loss of generality. Choose a subsequence. Then, and that's now the amazing thing, P of tau belongs to the stabilizer of mu, even connected component, because it takes on continuous, it's a polynomial, right? It's a continuous one parameter something. For all tau, let's say greater equal than 0, because of the fine genericity in terms of forward time. And that's quite useful probably, because it allows us to increase the stabilizer, increase knowledge about which elements preserve the measure.
And it's non-constant.
And it's non-constant because it knows norm 1. I mean, P minus the identity has norm 1. And the constant term of P is the identity. It's the limit of the Gn. So it's, yeah. It's interesting. That's the point. Exactly in the situations where it's not interesting. But we will come to that later. It's interesting because it's very general, but maybe it doesn't help you in all cases. Because this invariance that you got may not be quotation mark new invariance. Maybe it's invariance under the unipotent group that you started with. So that's the thing we have to fight afterwards, after we know that. That this becomes really new invariance and not old invariance. Yes?
Don't you need the yn and the xn to diverge, not to converge to the same point, the same?
Doesn't matter. That's fine. In fact, we will be able to choose xn equal to that one at the same point all the time.
Yeah, but if the yn converge to this point?
Yes? There's the speeding up which makes them move away from each other. Let me draw the picture. The picture is almost a groove. Okay, how does the picture look like? Well, one important thing is G mod gammas always look like this. Right? Because if G is SL3R, I can't really draw it, so just draw something that doesn't look compact so that I really can. this is the typical picture of G mod gamma because nothing else can be drawn. But it's helpful to think of if the cusp plays a role, it's helpful to have it in the picture. Good, then what happens? We have 2 points. We have the green point, xn. Let's drop the index, it does something. And the other point is very close together, very close to the original point. And it's not really doing anything for a long time, and then it starts to slowly drift away, and then it really moves away from the other orbit, and then we stop, because then we have reached the parameter Tn that depends on the displacement of the 2 points. And both of these things equidistribute in the whole space, which means I can't really draw it again because it's becoming too messy. With respect to the measure that we're currently working with, we never use anything special about the measure, only invariance and a codicity, so that we have the set of uniform and generic points. Now, here it's a bit too complicated. Let me draw it one more time, where I just draw the 0, tau equals 0, and tau equals 1 window. And I draw the polynomial, and you should think of that these values really live in the space somehow, but I draw the polynomial. Or they give me displacements of these 2 points in the space for the various tau parameters. So I have the green polynomial, well, I have one polynomial, which is somehow giving me the displacement. It's not 2 curves, it's 1 curve. Some parabola, something not so frightening because the degree is bounded. And I have a sequence of such things. So that's maybe my Pn, and I have more of them. And then I have a limit curve. That's my limit curve, say. Now, I'm claiming that this value here, some general tau, this P of tau preserves my measure. But this P of tau is a polynomial, it's a continuous function, right? So more or less on a small interval it's constant because it's a continuous function, right? Up to an epsilon it's constant. So I can think of, I want to use some of this value P of tau in a small interval around that point. And then further away, of course, I have to use different values of this P of tau. So I'm really interested in values close to tau in a fixed interval. Well, what's the size of the interval that I'm allowed to use? Well, it depends on your function. We take a continuous function and we want to test the invariance property using this continuous function. Right? We are saying that the values preserve the measure. Measures are functionals, so on the space of continuous functions. So to check that statement, we need to check whether 2 integrals are the same. And the 2 integrals are integral f d mu and integral x p tau d mu. That's the formula we need to check. And this we need for every f in CC of x. We have a continuous function of comfort support. So of course it's uniformly continuous. So f is uniformly continuous. And of course we want to prove this only up to an epsilon arbitrary. So for every epsilon greater than 0 there exists a delta greater than 0. With uniform continuity statement for this f. Now there's now a window between a small interval around tau minus kappa, tau plus kappa, where in this small interval around tau, the function p of tau is delta over 2 close to the value of p of tau. Let's make it p of tau naught. That's the point that we are interested in. And then we have the taus around it, and if we are very close to this tau naught, then we are well within the uniform continuity delta. But we also have uniform convergence on this compact subset 0,1 of the sequence Pn to p of tau. So we also get the following statement, namely by choosing this kappa and the n big enough, for all n large enough, we have the distance between Pn of tau and p of tau naught is less than delta for every tau in this small interval, tau naught minus kappa, tau naught plus kappa. Uniform convergence of continuous functions. That's all I'm saying here. Now let's think about what this interval means in this picture. From 0 to tau naught, this interval from 0 to tau naught in this picture is being speeded up by the parameter Tn. So it's giving you these two orbits that equidistribute in the space with respect to the same measure. Right? The green line equidistributes, the red line equidistributes with respect to the same measure. Where I stop here, say, I stop at tau naught times Tn. Why not? I can stop whenever, as long as the time where it stops goes to infinity, I have convergence to the limit. And the fact that I have a changing sequence of points doesn't matter because I have the uniform, the generic set of points that I've chosen. Now, let me stop not at tau naught n, but let me also stop at tau naught minus kappa Tn. That sequence also equidistributes, or that stretch of orbit also equidistributes. So I have two stretches of orbits that equidistribute to the same limit. But then the difference of the two stretches also equidistributes. Let me say it in a special case. Let me say it in a different way. Suppose you have a long orbit that equidistributes with respect to the space, and you chop it in the middle, and you know that the first half of this long orbit, for you, this half, also equidistributes. Then you also know that the second half equidistributes. Where the only important thing about half is that this second half that you're interested in is not going to 0. Well, it's kappa. It's a kappa portion. It's a fixed portion. So this is a very long portion here. This portion here equidistributes in space. But this red piece, the corresponding red piece of this portion also equidistributes in the space by the same argument. And the difference between the two, what is it? It's this. up to an epsilon. Who cares? Because up to an epsilon, the continuous function, we have this delta, right? We have this statement and the uniform continuity of the function f. So this small difference that we see from the value p of tau naught in this interval doesn't matter. That's the proof. And the more formal details are in the notes. Are there any questions to this? Yes?
Could you say a word on why we could call that H principle, which is quite a popular term in PDC? Is there any?
I think H stands for holocyclic.
Okay.
Any other questions? If not, let's thank the speaker and enjoy the break.